Hey guys, welcome back. Today we're talking about populations. This is part 2 going off last week. So, the learning goal for today. We're going to talk about carrying capacity again, as well as different growth models. So exponential, as well as logistic, and the associated curves of these growth models. The J-curve and the S-curve. We will also talk about what a niche is and competition. So this is taken from 5.4 of your textbook. When the size of a population reaches its carrying capacity, it is due to a number of different factors that limit the population growth. Last week we spoke about density-independent factors. These are factors that can affect a population's growth regardless of how dense it is, regardless of how many there are in a particular square area. And these examples are generally, you can think of them as due to chance, so floods or fires or droughts. This week we're going to talk about density-dependent factors. So these are factors that can affect the growth and population of a species because of how dense it is, because of how many there are. Density-dependent factors can be food, water, shelter, as they change in response to the population density. When you look at this list here, you see the word availability alone. That's because competition is one of the chief density-dependent limiting factors. As the density increases, the competition for these resources increases also. This is just a photo showing two different species competing over the same food source. So when organisms rely on the same resources, such as food, shelter, water, and space, they are in competition with each other. Organisms of the same species compete for mates in addition to resources. If two species are in competition and one is better adapted to competition, then the other species will eventually have to move out or it will die off. This brings me to the competitive exclusion principle. You can see this on the side here. It says that two species are unable to compete for the same resource in the same niche. So what is a niche? The word, whether pronounced niche or niche, it comes from the word nest. And it is a species' role in an ecosystem as well as its interactions. Interactions with what? Well, the ecosystem, that would be the biotic and the abiotic factors. You can think of what does it bring to this ecosystem? What is that species' role? What is its job there? That's its niche. So species either have to move or have to adapt if there is competition. So this is an image taken from the final exam, the mock stimulus. And it shows that on the axes here, there's two different conditions. There's temperature and then there's rainfall. And if we were to look at it and make sense, well, it shows there's a few different species here. And species A lives, its niche is in this particular cool temperature where there is very high rainfall. There is no competition with the other species here. But if you look at species C and species D, there's quite a significant overlap. And if we think about this overlap in terms of the competitive exclusion principle, which we have seen modeled in the field as well as in the laboratory over and over, then it says these two species cannot live here together. One will either die off due to the dominant species, or they will have to move out. Species either move to another habitat patch, and this is called spatial separation, or may be more prevalent at different times, so that is called temporal separation, so species can adapt to other species being in the area. Predation is another density dependent factor. And this graph here shows two different species. We have the snowshoe hare represented by the blue line, and we also have the lynx. So this is the prey, this is the predator. We can see that there is time on this scale, as well as population in millions on this scale. Immediate observations you may make is that, well, there's a lot more prey, snowshoe hares, than there are predators. And if you think back to our food webs, trophic levels, that's because energy decreases as it passes through the food levels. So there is a fewer number of them. You would also notice that there's peaks and there's troughs, and there's almost a bit of a similarity between these two species. The reason why we're seeing this is because predation is a density dependent factor. When the prey population decreases, the predator population also decreases. This cycle happens again and again and is represented in this graph. So where there is more prey, the predator population will increase also, causing, therefore, the prey population to decrease, causing the predator population to decrease, which then causes the prey population to increase and the predator population to increase, and this cycle goes on and on. So we have limiting factors here. Predation would not be the only one, as this snowshoe hare reaches its carrying capacity. Limiting factors could be, well, when there's more of them, there's a high density, there's a higher risk of diseases spreading throughout the population. And then they're also competing for food and competing for shelter. And of course, predation keeps the numbers in this cycle. If there is no limiting factor, a population will continue to grow exponentially at a constant rate, as you can see in this image here. If there is a carrying capacity, then a population will grow what's called logistically, showing limited growth. And it starts off growing at an exponential rate, but the rate decreases as it reaches carrying capacity. So, 5.5 of the text. If a population does not have any limiting factors, it will increase steadily as resources will be plentiful and predators, parasites, and diseases will be few. As more mates become available, the rate of growth will increase a lot, what is called exponentially. This will occur until the species realizes what is called its full reproductive biotic potential, and this is defined as the number of offspring capable of being produced by individuals of a species. This will continue indefinitely and rise without limit if it were not for limiting factors. However, each environment has its own carrying capacity, and carrying capacity is defined as the total population able to be supported by a particular environment. So I'm going to introduce two terms to you now. It's the J-shaped population curve and the S-shaped population curve. And the J shape is represented by this boom and bust cycle. The boom is where that growth happens exponentially for different reasons that we've spoken about already. It hits carrying capacity, and then that population, boom, busts, decreases at a very high rate. J because it kind of looks like a bit of a J letter with the flat up the top here and the curve, as opposed to an S-shaped population curve, whereby you can see it steadies out up the top here near carrying capacity. It slows down and then steadies out. And this graph here shows a bit more information on that. This may continue to fluctuate around carrying capacity, and that's something that we see in S-shaped population curves, as opposed to J-shaped population curves. The reason why we have a carrying capacity we can sum up being in environmental resistance. So this is the sum total of all environmental factors, limiting factors. So this could be competition for food, for shelter, for resources, as well as disease, predation, and all those other things. Check out 5.5 of the text for more information on this. So a few questions now. I'm not going to go through the answers in this video, but I'm going to allow you to pause the video to answer these questions so that we can go through them together in class now that we are meeting again. So again, taken from QCAA. Pause the video here. Flick back through if you need to and answer this question. Okay, again, taken from the mock stimulus, multiple choice. Pause the video and answer that. This is another multiple choice question. So there's a bit more to it now. So the figure below shows two different species. We just saw that, a model that looked a lot like that. Don't be tricked by the way that this question is worded. Think back to where did I see this and what was the context in which I saw that. So pause the video here. And then lastly, this is a short response question, so it's worth 4 marks as opposed to the others which are just worth 1. So this is an image that you'll see like in your textbook where we see boom and bust, we see fluctuation around the carrying capacities. So pause the video here, guys. Answer that one. You should give a few points for both A and B as they are both worth 2 marks. Refer to the data, refer to the stimulus in front of you. And all the best. And that is all for this video. So what I'd like you guys to start getting into now is, again, when we cover these videos, they are supplementary to your textbook readings. They're definitely not a replacement. They're more of a summary. So read over those 5.4 and 5.5 and also complete the check your learning questions at the end of them. Now that we have finished chapter 5 on populations, you can work through the entire chapter 5 review section. We will go over those questions in class. So all the best. God bless, guys. I'll see you soon.